So today we're going to be looking at stoichiometric calculations, but first let's have a look at the formula. So N equals to M on big M. So M represents moles, and the units for that is moles. And this over here is mass, and mass is always represented in grams. If the question you get in a test or in a worksheet gives the mass in something other than grams, you need to convert it to grams first. And this is molar mass. And molar mass are those numbers you find on your periodic table, and it's given as grams per mole. This equation here is given to you on your formula page, so you don't have to rote learn it. But you must get familiar with rearranging this to find different things. Okay, so let's have a look at an equation here. So this is the combustion reaction for methane. I have already balanced it for you. However, it's always worth checking if the equation given is balanced in a test. So here, let's have a look at this. So what happens if a question asked you to find the moles of CO2 given the moles of CH4, which in this case we're going to just say we have 1 mole. So we can use what's known as the stoichiometric ratio. So the stoichiometric ratio is the ratio of your balanced equation. So for example, for every 1 CH4, it will react with 1 oxygen to give us 1 CO2 and 2 H2O. So for example, if we have 1 mole of CH4, we will produce 1 mole of CO2. So that seems pretty straightforward, right? Okay, so let's look at another example. This time I'm going to write it in orange just to differentiate it. So here, let's just say we get given 0.5 moles of methane, and we want to find the number of moles of carbon dioxide produced. So what does that give us? So for every 1 CH4 we get 1 CO2 according to the stoichiometric ratio. So therefore, for every 0.5 moles we react, we're going to get 0.5 moles of CO2 produced because it's a 1-to-1 ratio. Okay, so let's have a look. What happens if it is slightly harder? So let's erase this. So this time, we're going to be given the moles of methane to be 0.5 moles, and they want us to find the moles of H2O. So this time we have a 1-to-2 ratio, which means for every one of this CH4 that reacts is going to produce 2 waters, which means the moles of water will be equal to 2 times the moles of CH4. Which is 2 multiplied by 0.5, which gives us 1 mole. Okay, so let's move on to something slightly more difficult. What happens if we want to find the moles of the CO2, but this time instead of given moles, we got given the mass. So the mass of methane is 0.5 grams. So what do? Well, to start with, since it's only the stoichiometric ratio lets you compare different things in the equation, we need to find the moles of methane first. And we can do that by using that formula we just looked at, which is moles is equal to mass on molar mass. So we have the mass, and we can find the molar mass. Therefore, let's just label this as step 1. The moles of methane is equal to 0.5 divided by 12.01 plus 4 lots of 1.008. So these numbers you can find on your periodic table. And if you plug that into your calculator, you'll get 0.031168 moles. Excellent. So step 2, now that we have the moles, we can use the stoichiometric ratio, which is a 1-to-1 ratio. So therefore, the moles of carbon dioxide will be equal to the moles of the methane, which means it will be 0.031168. And because this is chemistry, you have to leave everything in 3 significant figures in scientific notation, and to make sure you put the units in as well. So in this case, it would be 3.12 times 10 to the negative 2 moles. And I also like to underline your final answer just to make it a little bit easier for your teacher to find it. Okay, so let's have a look at another example. So I'm just going to erase this really quickly. So this time, we're going to get given the mass of oxygen to be 0.5 grams, and we want to find the moles of H2O produced. So step 1, once again, is you want to find the moles of oxygen. And a lot of time in chemistry, when you're doing a calculation, usually just start with finding the moles, which is always a good way to get at least 1 mark. So let's have a look. So moles of the oxygen, as you've been noticing, I like to label everything. I think it's really important to label things because it can get quite complicated and quite confusing pretty fast if you don't label things. So we got mass, which is 0.5, and it's in grams, over the molar mass, which is 2 multiplied by 16. And if you calculate that, that will give you 0. Let's just have a quick look. 0.5. That would give you 0.015625 moles. And then let's have a look. Let's do step 2. So now that we got the moles of oxygen, we can find the moles of H2O, which we know it's a 1:2 ratio. So it'll be 2 lots of that oxygen, which is 2 multiplied by 0.015625. And if you calculate that, you'll get 0.03125 mole. And once again, you got to leave that in 3 sig figs and scientific notation, which is 3.13 times 10 to the negative 2 mole. And just underline that. Okay, so let's take it one step further. So I'm just going to erase this once again. So let's look at a harder example. So what happens if we get given the mass of methane to be 2 grams, and we want to find the mass of water produced? So once again, step 1 is you need to find the moles because you can only use the moles to compare one chemical to the other chemical using the stoichiometric ratio. So let's have a look. So the moles of CH4 will be equal to 2 divided by 12.01 plus 4 lots of 1.008. And if you plug that into your calculator, you're going to get 0.12467 moles. Okay, so step 2 is now we can find the moles of water, which we know it's a 1:2 ratio. So every 1 moles of methane we consume, we're going to produce 2 moles of water. So therefore, the moles of H2O is equal to 2 lots of the moles of methane. So let's just put that in, and then we'll get 0.24935 moles. Step 3 is now we have to find mass. So once again, we start with this, and we can rearrange that to equal to mass equals to moles times molar mass. So let's just plug in all the numbers. So the mass of H2O is equal to the moles, which we have got in our previous answer, multiplied by the molar mass. I think I'm going to run out of space, so I'm just going to squeeze it in. Sorry, I know it doesn't look very neat. Okay. And if you equate that, you're going to get 4.49 grams. And then you underline it for your final answer. Okay, so now we're going to move on to a more complex example, but it's the same process. It's always the same process. That's what makes doing calculations in chemistry pretty straightforward. So what happens this time, we're going to use this equation here, which is aluminium reacting with an acid, which is hydrochloric acid, to give us hydrogen gas and aluminium chloride. So once again, I've given it to you fully balanced. So let's just say the question gives you the mass of aluminium to be 0.3 grams, and it wants us to find the mass of hydrogen gas produced. Once again, you always start with moles, so the moles of Al is equal to 0.3 divided by the molar mass, which is 26.98. And that gives us 0.011193 moles. Step 2. So step 2 is the challenging bit, because if you look here, the stoichiometric ratio is actually 2 to 3. So there's a couple of ways of figuring this out, and you just got to find the way that works for you. So I'll show you a pretty non-mathematical way of reasoning it the first time. So for every 2 aluminiums, you expect to get 3 H2. So we know we're going to use this 2 and the 3 somehow. But if you think about it, 2 is smaller than 3. So you would expect that if you consume 2 aluminiums, you're going to end up with more hydrogen gas. So therefore, the moles of hydrogen gas would be equal to 3 times 0.011193 divided by 2, because this will give us a bigger number, which is 0.01668. Okay, so that's a pretty non-mathematical way of reasoning it. But if you're curious if you want a more concrete mathematical explanation for it, let's have a look at that. So here, we know that it's going to be, so we know that essentially NaL is equal to 0.0111193, and we know that this is essentially 2Al, inverted commas, from the Stoich ratio. So if we just wanted the 1Al, I'm putting these in inverted commas because this isn't, it's not very stoichiometric-like, and you shouldn't write this down. This is just more for your understanding. You want to divide it by 2, right? So to get from here to 1Al, you want to divide it by 2. So now we have an Al to a 3H2. So now we can go 3 multiplied by 0.0111193 divided by 2. And that will give us the same answer. So here, in this first one, we know that it's going to be either 3 divided by 2 or 2 divided by 3. But because we expect to have more hydrogen gas than aluminium, we'll go 3 divided by 2. So that's a simple way of looking at it. And the, I guess, more mathematical way of looking at it is, so this one, 0.0111193, is 2 lots of Al, inverted commas. And if we wanted to make that slightly easier, we can divide it by 2, so divide it by itself to get 1 lot of Al, inverted commas. And then we can go 3, so every one of those, we're going to get 3 H2. So we get 3 multiplied by that 0.0111193 divided by 2. Okay, so it's all about just finding the way that works for you. Some people, if you like math, you're going to find that really straightforward, but other people might find it more complicated. So just find a method that works for you. So I'm just going to keep on with this. So now we have the moles, and once again, we just find the mass of H2. So we can go, so remember N equals to M on big M. So when we rearrange that, we get M equals to N multiplied by big M, which is 0.01668 multiplied by 2 lots of 1.008. And this gives us 0.03363, which equals to 3.36 times 10 to the negative 2 grams. And we underline our final answer. So once again, you can see that the process, so going moles to mass, so mass to moles to moles, and then moles to mass, is exactly the same as it was in the previous question, sorry. But here, the only challenging step is this bit here, is converting from a 2Al to 3H2. So sometimes that's probably the hardest stoichiometric ratio you can get. So once you do that, there's nothing really that can stop you. So once again, if you have any questions, feel free to message us. And I think now is a good time to have a go at the worksheet provided. I hope this helps you. All right, have a good one.